is to give you an overview of the obstacle problem, in particular the free boundary regularity for the obstacle problem. So let me try to explain what this is about. So I imagine the following situation. You have here a plane. It is Rn, and you have an extra variable R. So we are in n+1 dimension. And I give you here some sort of curve, some boundary. So you can think of it now in 3D for fix the picture. So it will be n equal 2. So we are in R3. And here you have this curve that represents a metal wire. And the idea is that to this metal wire, you're going to attach some elastic membrane. And essentially, the goal is to understand the equilibrium shape of the elastic membrane. Now, in this very particular situation, just with the metal wire elastic membrane, I can do the following. Let me assume that everything is a graph. So I will assume that I have a domain omega here. And then my metal wire is a graph over the boundary of the domain. So my metal wire is the graph of function f, where f is defined on the boundary of omega. And then my surface, my elastic membrane, is the graph of u, where u is a function from omega into r. So the fact that the elastic membrane is attached to the metal wire means that u restricted to the boundary is equal to f. So that's the boundary condition. So now the idea is that we have an energy, and u is characterized by some energy. So the u minimizes linear elastic energy. And this means what? It means that u is a minimizer of the following energy, integral over omega of grad v square, or let's say grad v square over 2. So this is the standard linear elastic energy with boundary conditions v equal f on the boundary. Okay, so this is very simple. It's just usual Dirichlet problem. So nothing very exciting happens. But now we're going to add an extra condition. We're going to add the condition that gravity is acting on our membrane. So I go back to my picture here on the top. And then I assume that there is gravity. So I will assume that there is gravitational force G here acting. So this will do the following. This will make my elastic membrane bend. So let me erase it. My elastic membrane will rather do something like this now because of gravity. Okay, it will be pushed down. How do I see this in the term of energy? In terms of energy, I have an extra term. So before I had only elastic energy, but now I need to add potential energy. So potential energy tells me that I pay proportional to the height. So the higher is my graph, the more I pay. So G is the gravitational constant, and V just represents the height of the membrane. Now, without loss of generality, I'm going to assume that G is actually identically 1. So I normalize gravitational constant to be 1. Okay. So now this is my energy. So G is 1. And now I'm going to add a third constraint. So the third constraint, and that's why we call it obstacle problem, is that my elastic membrane here is not allowed to cross the plane Rn. So now this plane Rn will act as an obstacle. And what does it mean? Let me try to do the picture again. So let's see. So I have my metal wire again. Let me draw the plane a bit closer now. And now my elastic membrane will bend because of gravity. And if the metal wire is close enough to the plane, then this metal wire will touch. And so there will be a region here where my elastic membrane touches the plane. So what is this? This is I'm still minimizing the same energy as before. So grad V square over 2 plus V over omega with boundary conditions V on the boundary equal to F. But now we have an extra constraint that V is non-negative. So the function V is not allowed to go below the plane Rn, which corresponds to the last variable equals 0. So this is Rn, this is my R, and Rn corresponds to xm plus 1 equals 0. And so my function V cannot go below, so it has to be non-negative. Okay, so now what can we say about this problem? So it's a nice variational problem. It's convex. So the minimizer actually exists and is unique. There is nothing, usual calculus of variation techniques, compactness, lower semi-continuity, blah, blah, blah. So existence of minimizers is easy, uniqueness as well. And the question is, what can we say about the minimizers? So the first thing you do for a minimizer is that you try to write the Euler-Lagrange equations, which means the criticality conditions. Now, look at this energy for a moment. So if you do the first variation of this energy, so if U is a minimizer and you didn't have without the U greater or equal than 0 constraint, so you remove the constraint, then you will have that the Euler-Lagrange equations would be just, so the first term is Dirichlet energy. It will give you a Laplacian of U. And the second term, the plus V, the linear term will give you equal 1. So you can compute just the optimality condition. You just, you test the energy with perturbations, and then you discover the following PD. Now, in this case, it's not this. It's not this because we have a constraint. We have this constraint, V non-negative, or U non-negative. So what does it mean? It means that here, maybe let me change color. Okay. So in this region, where here U is strictly positive, then we are far from the obstacle. We don't touch the obstacle. And essentially it's like if the constraint was not there. So in the region where U is strictly positive, you are like in the free constraint situation, and then the Laplacian is still 1. The point is what happens here, where you touch. And the idea is where you touch, in particular, look at this region where U is here inside the contact region. Here U is identically 0, which means that the Laplacian of U is identically 0. Just because, right? I mean, 0 function is 0 Laplacian. So motivated by this intuition, maybe you believe me if I tell you that in this case, our Euler-Lagrange equations are the following. Laplacian of U is the characteristic function of the set U greater than 0. So remember, the characteristic function of a set is the function which is 1 in A and 0 outside. So this means that if you are in the region U positive, I just wanted to do something else. So if we are in the region here, U positive, here in the region U positive, so here the characteristic function is 1. And where u is 0, the characteristic function is 0. So if I draw from the top the region, so this is my omega, there will be some region here where u is identically 0. Here is where u is positive. And now in this region, Laplacian u is 1. And then in this region, Laplacian u is 0. And actually, there is an extra condition which is hidden. Sorry, Laplacian u is 0 here. It's hidden in this PDE, in the following PDE, which is the following. So Laplacian of u is the characteristic of u positive, which is a bounded function, so it's an infinity. And because it takes values 0 and 1, so it's bounded, which means by elliptic regularity, then u is C1. So u is a non-negative C1 function. So u greater or equal than 0 and u is C1 implies gradient of u is 0 where u is 0. Right? Because you have a non-negative function, so at the minimum points, the gradient will be 0. So this means that my u has the following shape. So from the side, it looks something like this, u. So where it detaches, it has to do it with 0 gradient. Okay. So now the question that we ask ourselves, we have two questions. Question 1, how smooth is u? And question 2, how smooth is the boundary of u positive, which is our free boundary. So it's this region, the boundary of this contact set. Okay. So about the regularity of u, the answer to this question was given first in the 1960s. Frese was the first one, and then many others, but the answer is well known. And we know that u is C11, which means what? It means that the action of u exists and is bounded, but action of u is not continuous. So the function u is has bounded action at almost every point, uniformly bounded. But the action is not continuous, which is normal because the Laplacian is not continuous. The Laplacian of u takes value, it is not C0 because it takes value 0 and 1, it jumps. So the action of u is not continuous either. So that's the best you can hope for. And so the regularity of u is C11, and that's well known since now 60 years. Now comes the question of the free boundary. That's really the big challenge. So in this direction, there have been many results, but the first important result is due to Kinderlehrer and Nirenberg. And they proved in the 77 the following result. They proved that if you are in the following situation, that you have a ball of radius r around a point x0, and inside this ball, you see your free boundary. So this is the boundary of u positive. And the boundary of u positive separates here u equals 0 from, here u positive. So you have, it really cuts the ball in two parts. And so if you have this picture and the boundary of u positive inside BR of x0 is C1, then the boundary of u positive inside, let's say, alpha of the ball, so in here, is universally C infinity, actually analytic. So this is a sort of kind of Schauder type result that tells you that once you're a bit regular, you are very regular. You can kind of bootstrap regularity. So you get a very nice hypersurface here. But it's a conditional result because you need to know that you have a C1 hypersurface that is on one, and then this cuts into the domain. So on one side you have U positive, and on the other side you have U0. Okay, so that's the assumption. So these kind of points are the nice points where you can apply this sort of Kindle-Nirenberg result, and you have a sort of bootstrap type regularity. But it's a conditional result. Then Caffarelli arrived, also in around 77, and he proved the following, that the free boundary is the union of two sets, regular union singular. So you can split the free boundary in two parts. Regular points are points as in Kindler-Nirenberg. So these are points where you can apply Kindler-Nirenberg result. So these are points where you locally find a C1 surface that cuts in two, and then you are analytic. And then singular points are points where the set U equals 0 inside, so x0 is singular. It means that if you look at U equals 0 inside the ball of radius r around x0, this is very flat. What do I mean? It means that if I look at a ball, this is a ball around x0, which is on the free boundary, then I can find a plane and such that, and then I take a two translates of the plane. So this ball has radius r. The distance between these two planes is a little o of r. And my contact set, so what I drew before U equals 0, let me use the same color for consistency. It's all trapped in between these planes. So your function will look probably something like this. So this region is U equals 0. And then outside here, U is positive. So these are the singular points. And the amazing, let's say, achievement of Luis Caffarelli was that there is nothing else. There's just these two options. So just to give you an example, think of this. You have your domain omega, and then you have a free boundary that looks like this. Two drops connected by segment. In this case, if you zoom, this point is regular because you see that here on one side here, sorry, go with the wrong color. Yeah, here the blue region, U is 0, and then in the other half of the ball, U is positive. So you have a ball which cuts in two. Instead, if you go more here, this is a singular point. Because you see that in this case, the region U equals 0 is this tiny region. And then U positive is the complement. So this is regular, and this one is singular. Okay? So this is kind of the picture to keep in mind. You could have these big chunks where everything is nice and regular, and then there are these lines or these points where curves meet, and they form kind of cusps. And these are the singular points. Okay, so now we want to understand better this free boundary. So regular set, we said already is analytic. And singular, what can we say? Here I would like to let's say, discuss three questions. So question one, so how smooth is the singular set? Question two, how large is the singular set? And then question three, this is more of a different spirit question, but the philosophy is the following. So when you want to understand the free boundary, what you will always do is the following. You will take a point and you will start to zoom. So you will start to look closer and closer. You see, you look from far away and then you start to rescale and look closer and closer around a free boundary point. So this is what we call a blow-up procedure. You see here I'm going very close to the free boundary and then I'm looking closer and closer. As you zoom in, what happens is that you will see your solution. So first your solution is in a domain which is size 1, but as you zoom, as I'm doing now on my tablet, you see the domain becomes bigger and bigger because I'm zooming, so I'm looking closer, and then the domain omega becomes bigger. So as I keep zooming, my domain omega becomes bigger, keeps bigger and bigger, and eventually omega will become the whole Rn. So in this zooming procedure, you always end up with global solutions. So in the end, you can zoom in a lot and try to get to a global solution, function which is defined everywhere instead of being defined only on omega. And so the natural question that you end up here is, can we understand global solutions? Understand, sorry. Can we understand global solutions? Okay, so about question one, how smooth is singular? So in 98, Caffarelli proved that the singular set is contained in a C1 hypersurface. So he proved the regularity results for the singular set in the sense that the singular points are these points where you see cusps, and they cannot be scattered everywhere. There is a regularity in these singular sets because there is a global C1 hypersurface that covers everything. So the singular points have to kind of organize themselves. So this was the result by Luis. And now I will not discuss the techniques that are behind this. They require many tools. But of course, they don't say, I mean, the Luis could, back in the 98, he could not say whether there was C1 was optimal. So with time, we kind of try to understand, okay, how optimal is this C1 regularity there? I mean, for regular points, we have analyticity. And there has been a series of work, but I would say one of the starting point of this analysis was a paper in 2019 by myself and Serra, where we proved the following, that the singular set is contained in a C2 hypersurface up to codimension 3 sets. So what we realized back in 2019 is that if you want to prove regularity of the singular set, you cannot just hope to prove a regularity theory like for regular points that, you know, if you're C1, you're C2. You can try to bootstrap regularity, but eventually you have to give up on some very bad sets that where higher order regularity just fails. This is a bit like in minimal surfaces, but you know, in minimal surfaces, there are the minimal surface in dimension 8 can create kind of a very bad point. They can create conical singularities. Here is kind of similar. In dimension 3, you can create singular points where the structure is not C1, is not C2, but is only C1. So in 2 dimensions, you have C2 regularity everywhere, but in 3 dimensions, you start to see points in the singular set which are worse than the others. And this is optimal, this codimension 3. And then the analysis has been going on, and I would say it has been kind of concluded by Franceschini and Zaton, two former students here at ETH in Zurich, who proved that the singular set is contained in a C-infinity hypersurface up to codimension 2 sets. So if you want to get very high regularity, you need to throw away a bit of stuff. But once you're away, you're happy to throw away lower dimensional sets, you get a lot of regularity on the singular set. So these kind of cusps align very, very well, very smoothly. So this is kind of a very satisfactory picture, I would say, about the singular set. Of course, these theorems don't really tell us much about these higher codimension sets. And it's okay. There are partial results here. I would say rather good results here, but still it's not fully understood. So that's what I want to say about question 1. About question 2, I told you, okay, what about how big is the singular set? So if you look at this example, so the free boundary is a curve, so it's a one-dimensional set, and this is singular, all these points. So in this example, the singular set is a one-dimensional set, and the free boundary is a one-dimensional set. So in this example, the singular set is large. It's as large as the whole free boundary. They have the same dimension. So from this the example, it looks like, okay, you cannot say, I mean, in general, the singular set can be very large. But in 1974, Scheffer made a conjecture. He said, conjecture, generically, sorry, I'm unable to write. Generically, the singular set is empty. So Scheffer made a conjecture that what we are seeing in this picture is kind of not robust, which means that if I perturb a bit my data, the singular set should disappear. Let me try to formulate this in a more robust and mathematical, in particular, more mathematical way, because Scheffer didn't say what he means by generically. So let's think of the following. I have my metal wires to which I attach my membranes, right? And now let me take a one parameter family of metal wires. So I have my obstacle here. And now I move the metal wire up. So it means that I have my metal wire F, but I think that F is F0. And then I have a one parameter family of wires which are moving up and down. So Ft, T between -1 and 1, is a one parameter family of boundary conditions. I assume that they're ordered, f of s less than f of t if s is less than t. And now my original boundary condition, f is just f0. And then I move them up and down and ask myself, okay, so perhaps for my very specific boundary datum, I see a big singular set, but maybe as I perturb a bit my boundary datum, maybe the singular set will disappear. So I have now the solution to the obstacle problem here. So Laplacian of ut is the characteristic of ut positive. And now ut on the boundary of omega is equal to ft. So this is my one parameter family of problems. And I look at these problems and I ask myself, is it true that, let's say, for generic t, for almost every t, perhaps in Lebesgue sense, the singular set is empty? So question, is the singular set of ut equal empty for almost every t? This would be like a version of Scheffer conjecture. Now the answer is the following theorem. So yes, if n equal 2, this has been done by Monod in 2003. And then yes, if n is less or equal than 4, and it has been done by myself, Rossoton, and Serra in 2020. And actually we proved it better. We proved the following theorem. For almost every t, the n minus 4 dimensional out of measure of the singular set is always 0. So this means if you're in low dimension at n at most 4, this set must be empty. But it tells you also that if you're in higher dimension, perhaps it's not empty, we don't know, but it's very small. So generically, the singular set is very small within the free boundary. So the free boundary consists generically only of regular points, at least up to very lower dimensional sets. Good. So this is what we know so far about this problem. There are current attempts to push this dimension 4 to 5. It's still a work in progress here of Susanna Bertolini here at ETH. She's trying to push 4 to 5, but let's say we don't have yet an approach to get this in every dimension. Now, about question 3, the question 3 was the following, global solutions. So let me set up the following problem. Assume let u be a function defined in Rn, and let u solve Laplacian u is characteristic of u positive. So write it better, characteristic of u positive. And the question is, can I classify it? So I have a global function that solves this. Let's try to do it in this way. So let's think of this in this way. So you take Rn. Let's say that this is u equals 0. So u positive is the complement. It's all this region. So this is u positive. And do this. Interpret the characteristic of u positive as a source term. So let rho be the indicator function of u positive. So this is like constant density equal to 1 in the positive region. So it's like putting constant mass there. Then we know that the Laplacian of u is rho, which means that u is the gravitational potential generated by rho. I mean, I'm just using Poisson law, right? So if you give me a density of mass and you solve the Laplace equation, you get the gravitational potential generated by the density rho, which means that minus gradient of u is the gravitational force generated by rho. What does it mean? So the gradient of, so it means you think of this uniform density of mass in the complement of u equals 0, and then you look at which gravitational force it generates, and then the gradient of u tells you this force. But now let's look at the picture again. Here I have u equals 0, which means the gradient of u is 0. So inside the contact set, the gravitational force is identically 0. So having a global solution to the obstacle problem is the same as looking at the following. You put constant density here in the complement. You call this density rho, which is identically 1 there. You look at the gravitational force that it generates, and inside the contact region, so in the complement where rho lives, there is no force, no gravitational force. And then you ask yourself, okay, which examples can you build like this? It looks very rigid. Well, so in this direction, actually, there has been a lot of work since several years. So the first theorem in this direction is due in 1678, is due to Newton. So Newton proved the following theorem, that if you take a ball, actually a sphere, and you put constant density on a sphere, then this density will generate no gravity inside the sphere. This is the no gravity in the shell theorem by Newton. So Newton, in 3 dimensions, he proved that u equals 0 can be a ball. So a ball is a possible solution to the obstacle problem. So you have u equals 0 is a ball, and then u is radial outside. So that's the first example of contact set you can get for a global solution. Then in the beginning of 19th century, actually then a bit before 1800, and then some works later, there have been two papers, one by Laplace before 1800, and then one by Avery a bit after, and they proved that U equals 0 can be an ellipsoid. So by calligraphic E, I will denote an ellipsoid. So you can have balls, you can have ellipsoids, but you see that if I can have an ellipsoid and I center an ellipsoid so to pass tangent to the origin, and then I rescale an ellipsoid around the origin, so I make it larger and larger. In the limit, as I rescale it, I will get something like this. So an ellipsoid, as you rescale it, it becomes bigger if you zoom it around the boundary point, as in the picture, and then you will get a paraboloid. So if you just take the work of Newton, Laplace, and Avery, you discover that global solutions of the obstacle problem are in correspondence to say that U equals 0 is either an ellipsoid, a paraboloid, or a trivial extension of them, in the sense that you take an ellipsoid in k dimension, cross r n minus k, or a paraboloid in k dimension, cross r n minus k. So you can always add artificial variables. You take a solution in Rk and then you add fake variables. So you have always these solutions. And the question is there anything else? So so this is an example, a list of solutions. And then the question is this everything? So can we classify global solutions? Is there something else? So this is a question that has been started and been investigated since the 1930s. So in 1931, Davis proved that if U equals 0 is bounded and dimension 3, then U equals 0 should be an ellipsoid. So in 3 dimension, if you look at bounded sets U equals 0, then you cannot find anything else but ellipsoids. Then in 1986, by work of Di Benedetto, Friedman, and Sakai, not all together, these are two papers, they proved the same result but in arbitrary dimension. So if U equals 0 is bounded, then U equals 0 is an ellipsoid. Then a bit before, in 1981, Sakai proved that if n is 2, then U equals 0 can only be an ellipsoid or a paraboloid. So there is nothing else in 2 dimension. So the problems with Sakai proof in 2D, sorry, n equal 2, is that it's based on complex analysis techniques. So it's very 2-dimensional. So then this says that if there is a counterexample to this classification, this should happen in dimension at least 3, and the set U equals 0 should be unbounded. But then in 2020, Eberl, Weiss, sorry, Shagolian, Weiss, first Shagolian. So Shagolian, Weiss. They prove that if n is greater or equal than 6, then U equals 0 must be an ellipsoid or a paraboloid. Or, okay, artificially you can add fake variables, but let's say essentially again, everything. So when I say n greater or equal than 6, what I mean is the following. So if you have a 6-dimensional solution or a higher dimensional solution, which is truly six-dimensional, which means that it's not that you cannot take a three-dimensional solution and just add three fake variables by making constant in three extra variables. That's not allowed. It should be really a function that depends on all six variables or more. Then you have the classification. And finally, then in, I would say 2024, Eberl, myself, and Weiss prove that if n is greater or equal than 3, then u equals 0 is either an ellipsoid or a paraboloid, or of course the trivial extension where you add fake variables. And that's it. So this shows that you cannot have anything else. So the full classification is now closed. Maybe the idea is that I will to stay in 45 minutes, so I will essentially wrap it up now. But this is an interesting problem because very often we're used in PD is that the higher the dimension, the worse it should get. And in this case, it's the other way around. The higher the dimension, actually, the easier it gets. N equal 2 is special. Okay, is a kind of a different situation. But let's say if you go from dimension 3 and higher, the three-dimensional case is the most difficult one. 4 and 5 are slightly are much easier. Are much easier than 3. And then from 6 down, it gets even easier than 4 and 5. And you could ask yourself why. And this is so the difference with respect to local regularity is that here we have global problems. And so there is a lot of issue about integrability at infinity. So because you have to integrate functions all the way to infinity because you have global solutions. And now you can just do the following exercise. You can take in Rn a parabola. So this is xn. This is x prime in Rn minus 1. Let's you take the classical parabola. So you take x prime square less than xn. Okay, so this is my domain. You'll call it P. And then you ask yourself, what is the solution? So question, I want to solve Laplacian U equal indicator function of P. Okay, because that's what essentially you're doing in many of this problem. So not Laplacian U, let me call it Laplacian V. Sorry, let me give it a different name. So if I ask you what is the solution of this, your first temptation would be to say, oh, let me just use the fundamental solution of the Laplacian. So the first guess would be, okay, V of x should be the convolution between the right-hand side and the green function, where g is up to constants, 1 over x to the m minus 2, up to dimensional constants. So this should be the integral over P of 1 over x minus y to the m minus 2 dy. Okay, so if you think that you can invert with the green function. And now you take this integral and you say, is this really the solution? Let's say up to harmonic functions. And it turns out that this integral, so this is a non-negative function. So there are no cancellation that can happen. So it's not like you can have plus infinity and minus infinity and you need to integrate in some smart way to have cancellations. No, this is just, you're just integrating a non-negative function on a domain. So you can just check whether this integral converge or not. And this integral is finite if and only if n is at least 6. So you can just integrate in polar coordinates in some sense, so or let's say cylindrical coordinates. So you take your axis xn, and you take the cross section here. And first you integrate the cross section by cross section, then you go in the other direction. You don't need to do a very precise computation. You can just do up to multiples, and then you see that this integral only converge in high dimension, in particular in dimension at least 6. And this 6 is exactly why in the first paper by Eberl, Shagoli, and Weiss, they prove result from dimension 6 on, because they use this representation formula, which is false in dimension 3, 4, and 5. Now, if you're in dimension 3, 4, and 5, you need to adjust the representation formula, because this is not correct. This creates extra difficulties, and in particular, dimension 3 is where the challenges gets the worse because this function v behaves in a very weird way. It becomes like so in some variables. So in dimension, so the problem is that in dimension 6, so if n is greater or equal than 6, v is bounded. And then instead, if you are in dimension n equal 4 and 5, you can find a new v, not this one. You have to twist it. And v is not bounded, but it grows like almost linearly. So v of x is bounded by constant 1 plus x. So you find a solution which is not bounded, but it has almost linear growth. And then if you're in dimension 3, then v at x at infinity will behave like x log x for x large. So there are some logarithmic divergence at infinity. And that's what creates extra complication in the analysis. And yeah, so that's just to explain why the dimension makes such a difference. And okay, so I hope at least I gave you an overview. Of course, I didn't enter into technical details, but I wanted to show different aspects of the problem. And I hope at least I could convey some of the directions that are definitely important on this problem. So I think I will stop here. Thank you.